Please welcome our panel, How AI, ML, and Motion Planning Testing Are Advancing New Mobility, with Chris Barker from CBC Transportation Consulting, Jinhua Zhao from MIT, and John Dolan from Carnegie Mellon.
Hello, and welcome to our afternoon webinar session on how artificial intelligence, machine learning, and motion planning testing are advancing new mobility options. My name is Chris Barker. I'm CEO for CBC Transportation Consulting. And today I'm joined by two esteemed colleagues who are going to add for a great conversation. First, I'd like to introduce Professor John Dolan, who is the Principal Systems Scientist at Carnegie Mellon University and Carnegie Mellon University faculty for the Argo AI Center for Research for Autonomous Vehicles. Welcome, Professor Dolan.
Thanks very much.
I'm also joined by Professor Jinhua Zhao, who is lead for the Urban Mobility Lab at MIT University and is focused on city and transportation planning activities. Welcome, Professor Zhao.
Glad to be here.
So both of you have had tremendous contributions to the autonomous mobility market, and I'm excited to kick off a discussion that looks at your collective work and where we're headed in this industry as we move forward. And I'd like to start, Professor Dolan. So you and your team at Carnegie Mellon won the DARPA Urban Challenge in 2007 for demonstrating what's possible in autonomous mobility, navigating an autonomous vehicle through multiple urban driving settings. When you look back to that initial development, which was huge for the industry, how would you describe our progress today and what's been accomplished in autonomous vehicle design and operations since the DARPA challenge? And what are the big accomplishments and what are the lessons learned so far?
Thanks, Chris. That's a great question. I'll mention a number of things. The first one is pretty trivial, I guess, but there's a cosmetic change. Back in the Urban Challenge race, we had lots of stuff hanging off the vehicle, sensors mostly, and those have been zipped into the body of cars nowadays. So sounds trivial, but it shows that the researchers have been working with the autonomous driving companies and using the practices that have been developed over more than 100 years to make them look like showroom floor vehicles. But more importantly, there are a lot of things we didn't take into account in the Urban Challenge. We are now traveling at higher speeds. The limit back then was 30 miles per hour. We didn't have to deal with pedestrians. We didn't have to deal with GPS dropouts, or at least we were in an environment where they were much less likely than a lot of the environments in which the cars are driving today. We didn't have to deal with dense traffic, although we were interacting with traffic. We didn't have to deal with traffic lights. So those are a lot of examples. So now much of the progress has been made in dealing with more complex situations and handling all those things, and even some others that I didn't mention that we didn't have to worry about then. Another thing is that the pipelines that we created for the testing and the development have been now matured and become pretty solid practice within the industry, and so they're being used very productively in order to test, log, and iteratively and incrementally improve things. Another big one that we'll probably have an opportunity to talk more about is the application of deep learning to revolutionize perception in particular, but then also be applied also to behaviors and motion planning. And then there's been some minor progress, but I'd say not substantial, in dealing with bad weather and bad road conditions. And then in answer to the last question that you asked about what or let's see, did you ask me something about lessons learned?
Lessons learned, exactly.
Yeah. So I think the biggest lesson learned is that it's a lot harder than we thought to create sufficiently safe and reliable autonomous vehicles that can be fielded confidently and with acceptance by the public.
Very good. And conversely, Professor Zhao, you're leading a team at MIT that is looking at autonomous mobility and what is required to prepare our cities for this next generation of transportation technology. In parallel to Professor Dolan's comments, can you talk a little bit about how you would assess the readiness of cities and these urban environments that are starting to see more and more autonomous vehicles being introduced? And where are we in that continuum of being ready? And conversely, what are some of the lessons we're learning in that process as well?
Thank you. I'm glad you asked this question, right? There are two parts of the story. The first part is make the machine work, right? The second one is how does the machine fit within the mobility system? how does it interact with people, and interact with the urban environment, right? So here, I want to bring the discussion from a technology perspective to a behavior perspective, and then further to an urban perspective, right? So I'll pick one thing first, which is what a city is good at. I mean, city pride itself at encourage and enabling social interaction, right? So here, how would this machine, this autonomous vehicle, interact with the other component of the system? I think that's the key really, both the challenge, but if we solve the challenge, that's I think the main breakthrough. And actually Zhang's work is very much on this anthropomorphic autonomous vehicle, I think very much contribute to this area, right? That's a major difference between the DAPA example versus when you apply the vehicle in the urban context, right? The second thing I will describe this from mobility system point of view. Autonomous vehicle cannot work alone, right? It have to be a component of a multimodal system. Mm-hmm. Particularly if you're talking about the bigger cities where you have a public transit, railways, buses, bicycles, pedestrians. How would AV interact with any one of this and also be one of the components to the broader system? I think that's another really important point to emphasize. The third one, I do want to talk a little bit about from the policy angle. The federal and the state government, typically they worry about safety, they worry about emission. While it's the local government, they talk about congestion issue, they talk about livability issue, they talk about equitable issue, right? So the AV discussion, I think mostly from technical side, we'll look at how to make it safe, how to do low carbon. Mostly AV will probably be electric vehicle, et cetera. But when it comes down to the municipal level, the city will care about how does AV contribute to my solving the congestion problem? How does it contribute to solving the mobility equity problem, right? How does AV bring in the city being livable, right? That's the type of kind of challenge that we are adding to the discussion here.
Some great points there. I kind of want to unpack a few of those. So Professor Dolan, you talk about what's possible back in the early days of the DARPA challenge. And now so many things have evolved, whether it be the technology, the cities themselves, the policy component. From both of your points of view, where are we at in terms of as far as moving toward more broad adoption and the readiness of the city's infrastructure and the policy components and the vehicle functionality and design? How are we doing there, and where are the hurdles that we still have to kind of overcome?
Shall I go first on that one?
Sure, please.
Okay, sounds good. So I think to put it in a broad context, I think it's accurate to say that it's a lot easier to do things on the highways because they're just less complicated environments than in the cities. So that's one principle. And for that reason, I think that something like long-range trucking, which obviously also has a pretty strong business case, is more likely to reach some level of maturity before the use of these vehicles widely in the cities where there's so many more complicated environments. Now, there are a good number of hurdles. I'd say the biggest one is related to what I said before, that is providing sufficiently safe and reliable vehicles. I think that it would be unlikely that the public would accept a level of safety that is comparable to the current one that we have with human drivers, which involves about 37,000 deaths per year from accidents in the United States and 1 million worldwide. So I think people generally expect automation to do better than that, and we need to be able to show and provide guarantees, if we can, of that. A few other things are handling what we call long-tail distribution types of issues, like things that don't come up very much, and being able to handle things that have been unseen before by an autonomous car. HD map generation is something that's very important right now, but it's not easy to do because things change very rapidly in the urban environment. So you have to be able to update that effectively and efficiently. And then there are a whole bunch of things having to do with sensors. Sensors need to get less expensive, LiDAR in particular, and to be able to do effective sensor fusion remains a challenge. So I'll stop with that. There are several as I could talk about, but I'll turn it over to Jinhua.
Sure. Yeah. Thanks, John. First of all, pick up John that started with on the safety side, right? There are some technical progress on that. For example, Mobile, they developed this notion of responsibility sensitive safety, right? Try to have a more precise notion of what do we mean by safety definition here. Then there's also the side of public perception of safety here, right? For that, let me add one side. We did a kind of a global comparison among 50 countries. Look at how do people, as of today, think of the AV, right? Are they safe for you now? Or how long does it take to fail? What we find is the following. We find in many of the developing countries where the current mobility safety is very bad, they actually have a more rosier view about AV. Potentially, my interpretation this, right? People put safety in the relative term rather than the absolute term, right? The situation where the safety as of now is so bad, people have a lower bar, a lower expectation, right? So AV, if it beats the current status quo, then I probably I will embrace it. Versus a situation where you already have a very high standard. That's to beat that, it was much more challenging, right? Give an analogy here. In airline industry, particularly in the US, the safety is really good. It's a superb level, right? So do the society expect that level of safety as an airline industry? Do we impose this upon autonomous vehicle on the ground? Or do we tolerate something? The reality is in the US, we have 100 people killed per day. I guess reality would be between this zero tolerance to another 100. And somewhere, this will be a social norm balancing here.
So to that point, I want to talk a little bit about the technology that is enabling these systems to operate and hopefully operate safely. Let's talk a little bit about artificial intelligence. So when you look at artificial intelligence and machine learning, which are both required to successfully operate autonomous vehicles, and all the thousands of computer driving scenarios that have to be looked at and analyzed and determined how to properly and safely move these vehicles through city streets, how would you assess the progress in advancing more AV vehicles onto the roadways with the artificial intelligence capabilities and the machine learning capabilities that we have today? And what do we need to look at for advancing that functionality as we go forward?
Yeah, I can make a few comments on that. I think, well, I had alluded to deep learning before, and it's become a buzzword which gets bandied about in the press. But it's been remarkable what it's enabled to be accomplished. So, for example, whereas in the past we were using exclusively what we call bounding boxes, just rectangles around cars or other objects that we've identified, you can actually do with deep learning, pixel level in an image, segmentation of vehicles and get a much better understanding of their shape and the direction they're pointing and things like that. And there are a lot of other examples of deep learning being applied to significantly improve perception, which of course is a very important component of safe and effective driving. And I think, as I mentioned also before, those are being applied more and more to other tasks within the stack, like behaviors, where you're trying to make a decision as to whether or not it's your turn to go at an intersection or deal with what's not really fully regularized, an unprotected left turn, right? You're trying to decide whether you can turn in front of somebody or go behind them, and that's one of the instances in which a lot of accidents occur, for example, in autonomous driving. So I think learning will be helpful in terms of looking at this with a high level view, giving us the ability to move more in this direction of doing verification, because it's very difficult to come up with a set of rules that's going to cover every possible instance, whereas learning has expanded that envelope somewhat. However, I'd say that we still are not at the point of having a silver bullet on how to provide safety verification and absolute safety for vehicles.
Yeah, on that, I would add two more questions. One is on the interability discussion, right? This is a generic discussion on all mobile machine learning AI. The second one is robustness, right? Both are quite relevant in the autonomous vehicle context. And there are a group of scholars try to, first of all, introduce what notion of interability, what do we mean by that? And improve this interability so that as a user or as a system, we trust this decision-making process, right? The second one is robustness of the algorithm, right? That's another kind of often use criticism to the machine learning. But for that also, there are a lot of new research try to improve the robustness of the AV, particularly in this safety critical context, right? Mm-hmm. For that, I want to add two more things. One is there's a Daniela Ruth's work at CCO at MIT, try to introduce this notion of a personality of a vehicle, right? So you can understand the other vehicles' degree of aggressiveness And depending on your understanding of this vehicle, then I adjust my behavior differently. Right. So last one, I just add one still a major challenge is this social intelligence, right? Suppose I'm a AV, I'm trying to turn right. There's a pedestrian crossing here, right? In a human driver, we kind of have an eye contact with each other or a small gesture. We understand the intent, right? So either the pedestrian go first and the car go left. So this type of negotiation, people are just intuitive about it. So we're very good without any effort. But right. To empower the machine to have this social intelligence, I think still really a challenge.
Professor Zhao, I'm really glad you brought this up because, oh, sorry, go ahead.
Well, I was just going to key off a couple of things there because I think those are great comments by Jinhua. I just wanted to mention that some of the things we're working on in my lab have to do with similar things where, for example, we look at ramp merging, which is trivial if you're far apart from one another at the merge point. But if you're close, then you need to do some kind of negotiation. And as Jinhua was mentioning, that could even be done visually. But in any event, it needs to be done in some way where you determine whether or not that other car wants to yield or not. And it's harder than it sounds, I guess I'll put it that way. So we've been working on using machine learning techniques in order to handle that kind of thing.
I'm glad you bring this up because one of the things I've been thinking about is, you've got human-driven activities, and Professor Zhao, as you were describing, where there's gesturing and there's recognizable things happening that are influencing decision-making for drivers and pedestrians. And then we have human or machine-driven vehicles. And I know, Professor Dolan, you talked about previously some of the work you're doing around motion planning testing and trying to kind of predict human behavior and what might happen in relationship to the development of these autonomous vehicles. Can you talk a little bit about what that motion planning testing is helping you uncover and how it's making the vehicle movements more predictable and safer?
Sure. I'd say that the basic assumption it's based on is that we're going to have both human-driven and autonomous vehicles on the road for some time. So you need to be able to do socially cooperative driving. And there are particular instances where that's most important. One is intersections, and that's where the most accidents happen. Another one would be lane changing on the highway, ramp merging that I already mentioned, and traffic circles, for example. So we're using a variety of machine learning techniques. One of them is called probabilistic graphical models in order to try, in the ramp merging case, to project or predict whether or not a person is going to yield. And we're using reinforcement learning. That's got some challenges with it. One of them is that it requires a lot of testing. The other one is that the testing really shouldn't be done on a real vehicle, or at least most of it shouldn't, because you can have failures where you're going to hurt people or at least hurt the car. So that brings up challenges of making the simulation sufficiently realistic. And that faces the challenge of having sufficiently realistic human driver models, which at this point we don't have for the general case.
And on the same token, Professor Zhao, how is the research that Professor Dolan is referring to, are you seeing that coming into city applications where there's a cooperative engagement between the cities and the folks at the university and industry to further advance this kind of testing?
Right. Maybe I try to take it more broadly, look at this, the transitional period between AV and a human driver will be decades long, right? Will be different degrees of mixture here. At MIT, we have another professor, Cassie Wu, and together with the Berkeley professor, Alex Bain, they've been looking at how do we treat AV not only as a controlling device of itself, but as a controlling device of the whole traffic, right? So almost treating the AV as a moving traffic light. Right. So you use the AV, you may only have a 2% penetration of the traffic, but the AV, we impose upon it an authority, right? You also have the duty to control the whole traffic flow, right? That's a very interesting story there, because if that can happen, then we do not need to wait until a high penetration of AV in the traffic to really improve the overall system condition there.
And that's absolutely fascinating, because now we're getting more efficiency and better traffic throughput. Are there examples of that where in the US or internationally, how that is being applied, and any lessons learned from that so far?
We have, oh, sorry.
Oh, sorry. But go ahead, no, please.
Well, this is relevant, I think. I saw, Jinhua mentioned Kathy Wu, and she had given a talk at CMU before, and her work was very interesting. Something somewhat related to that has to do with smart traffic lights. And one of my colleagues is working on that kind of thing, and has actually shown experimentally that in the city, in a particular route of traffic, which is pretty busy, the throughput can be increased using his techniques of scheduling.
Very good. So a comment or a question I have for both of you is, as leading research universities, what other mobility challenges are you trying to tackle beyond some of the subjects we discussed earlier, but just looking at this bigger ecosystem that we're trying to design for? Are there other things that your teams are trying to tackle and understand better that is going to further advance some of the work on the AV side?
Go ahead, Jinhua.
Sure, yeah. So a couple of major topics. They are not necessarily on AV per se, but more broadly. One is how do we decarbonize the whole mobility system? Right. That would say the major. I would say probably the most significant ones. If we're really serious about this COP26 or our climate change goal, mobility is the biggest CO2 emitter in the United States, right? How do we decarbonize that? There's a major effort. There's a lot of electrification innovation. There's all the way from battery design, then to the charging location choice, et cetera, the whole spectrum of work there. And AV should be a part of that story, right? That's one thing. The second one, maybe I also end here, is the mobility equity discussion. Right? Mobility system, at least urban mobility system, as of today, we are failing in terms of mobility equity, right? A large chunk of the population, either the disability, income, health, all these reasons, they do not enjoy enough mobility and accessibility, right? So whatever AV and EV to do, we hope that this technology can enable to really fulfill the goal of access for all, and as the social agenda here, right? But that's not easy, because just like most new technology, when it happens, it doesn't care about equity. It cherry pick the market wherever we can make money to survive. And when it's successful, then you try to penetrate the whole society. But today is a different era. We have to, on day one, talk about the equity here, right? So that also relates to a particular question, which is a private-owned vehicle model, whether it's autonomous or human-driven, or a fleet-based or service-driven model there. In that model, it's more likely to achieve equity objective that way.
That's an excellent point. Really important. Professor Dolan, thoughts on your side?
Those are great comments. We have some similar projects going on having to do with access and, for example, using smartphones to provide up-to-date information on bus routes that help to make transportation more efficient. Another one is bicyclist safety. We've got a project going on in that. And we have some we've got a university transportation center that is sponsoring a lot of these types of transportation, urban mobility types of projects.
I have one last question with the time we have left, and I just want to get your individual input on this, is how can industry and cities work with your teams more to unlock further breakthroughs in mobility as we move forward? Any advice you have for industry and cities of how they can engage Carnegie Mellon, how they can engage MIT and some of your peers across the country?
John,
Professor Zhao, you want to take that first?
Oh, okay, sure. I would. So at MIT, we set up this new institute called MIT Mobility Initiative. 50 professors from 12 different department centers come together, try to offer a cross-disciplinary response to mobility challenge, right? In that, we have one reservation, which is different organizations in the society have a different degree of risk tolerance, right? Public sector, the lowest, for good reasons. Their priority is stability, right? Private sector, higher, but still have a bottom line to guard. But academics and university should have the highest risk tolerance. In many ways, like Professor John Dolan and myself, we are paid to fail so that other people do not need to, right? So here at MIT and at Carnegie Mellon, we are envisioning mobility systems that do not exist today, but could exist tomorrow, right? So therefore, this industry and academic collaboration, I think, will be essential for us to solve this problem.
Excellent. Professor Dolan, you get the last word.
Well, we've got some similar initiatives at CMU. They're focused primarily on mobility within Pittsburgh and Pennsylvania in general. We've got a collaboration with the University of Pennsylvania. And this University Transportation Center that I mentioned before is an ongoing effort. And it's a little bit unusual in that the majority of university transportation centers, which are sponsored by the Department of Transportation, have been at large land-grant universities, been centered on the civil engineering department. In our case, it's focused on not so much traffic patterns and the kinds of things that civil engineers do, but more on applying our strengths in computer science, robotics, data science, machine learning to mobility solutions. And so if people want to get involved with that, there are a lot of opportunities, and we see collaborations with the transportation sector and with people who have good ideas about how to improve the overall urban mobility environment.
That's fantastic. We are unfortunately out of time. I want to thank both of you gentlemen for your contributions to today's discussion. I think we could easily talk for another hour, but we'll look forward to continuing the conversation offline. Thank you all for joining today's session, and we look forward to keeping in touch. Thanks
It's a pleasure.
much.
Thanks.
Thank you, Chris.
See ya.
And
Thank you.
really good to talk to you, Zhao.
Likewise, Jinhua. See ya.